Yes, we can start by reviewing this very important reaction of chlorine, and this is on oxidation properties chlorine. Uh, this is on oxidation properties of chlorine, and the oxidation is in form of displacement. We remember the order of reactivity. We remember that the order of reactivity decreases as you go down the group, and the first element in the group is fluorine, followed by chlorine, followed by bromine and iodine. So the order of reactivity decreases in that order. Now, reaction of chlorine with potassium bromide. This is one of the questions I had asked you in the test, and you can assess yourself if you passed it. Now we always get the answer from the equation. Let us look at the equation. If I have potassium bromide solution, we agreed this solution is purely colorless. I have potassium bromide solution which is colorless, and I add chlorine gas, then chlorine is going to displace the bromine. Chlorine is going to displace the bromine and it will take its place. So we form potassium bromide. But don't put here potassium chloride and you put Cl2, that because the chlorine atoms are 2. No. For the compound, remember the valence of potassium is 1 and the valence of chlorine is also 1. So the correct formula of potassium chloride is that, then plus bromine liquid. Remember we said these halogens at room temperature, they exist as diatomic molecules. So when we are writing bromine, we should give it its 2 and we say Br2. So this is the equation. Now, potassium bromide is colorless, potassium chloride formed is colorless, but bromine is red. That's why we said that the colorless solution will turn to red. What is red is bromine. What is colorless is potassium bromide and potassium chloride. But if you have a mixture of red and colorless, then the whole solution will become what? Red. However, I wanted you to understand the explanation, because most of the time when we ask this question, we shall say, explain your observation or give a reason for your answer. And the simple explanation we are giving is that, remember, who can tell me the simple explanation for this reaction? Someone who has been attentive. Why does the colorless solution turn to red? Who has a simple explanation? Come on. Come on, come on. I want an explanation. Why does the colorless solution turn to red? Who can explain? Potassium bromide is colorless and it turns to red. Yes, is it Dylan? Speak louder.
Chlorine is more reactive than bromine.
Good.
So it removes.
Don't say it removes. No, nada. Repeat, start afresh.
Chlorine is more is more reactive than bromine.
Yes.
So it displaces bromide ions from potassium bromide, forming a solution of potassium chloride, and a red liquid of bromine.
Forming potassium chloride and a red liquid of bromine. Now, Dylan, I said we have two ways of saying this. If you have said chlorine is more reactive than bromine, then chlorine displaces bromine. Are you getting that? Are you getting that? You can also say chlorine is a stronger oxidizing agent than bromine. Chlorine is a stronger oxidizing agent than bromine. Therefore, chlorine oxidizes bromide ions to bromine. When you use bromide ions, you say chlorine oxidizes bromide ions. But chlorine does not displace bromide ions. So when you use chlorine, you say chlorine displaces bromine from its solution of potassium bromide. Let me repeat it for you such that in case you are writing down something, you can take it down. We say chlorine is more reactive than bromine, full stop. And you saw how I was marking. I gave you a mark for that statement. You remember? Chlorine is more reactive than bromine. That is the first statement. Therefore, chlorine displaces bromine from its solution. Therefore, chlorine displaces bromine from its solution of potassium bromide, forming. Therefore, chlorine displaces bromine from its solution of potassium bromide, forming bromine, which is red. That is the explanation. I repeat it. Chlorine is more reactive than bromine. That's the first mark. Therefore, chlorine displaces bromine from its solution of potassium bromide, forming bromine, which is red. Now, that is the same thing that occurs with iodine. If you have potassium iodide, chlorine will displace the iodine and it will form iodine as a liquid, and iodine is dark brown. So in this case, your observation is going to be a colorless solution turns to a dark brown solution. And what is dark brown? The dark brown solution is for iodine. But on standing, a black solid will settle at the bottom. After some time, a black solid is deposited as iodine at the bottom of the beaker or test tube, whatever you'll be using. So, who can tell me the explanation for this observation now? A colorless solution turns to a dark brown solution. Someone tell me the explanation. You don't want to talk? You don't want to talk? Who is talking? I need an explanation for this. The colorless solution turns to a dark brown solution. Who can explain for me my observation? Isaac.
Teacher, since chlorine is more reactive than iodine, it displaces iodine from its solution of potassium iodine.
Potassium iodide.
Yes, and this causes potassium chloride and iodine gas, which is a black solid at room temperature.
You see, you are mixing. You have just said iodine gas, which is a solid. Sorry, but thank you. Chlorine is more reactive than iodine, and therefore displaces iodine from its solution of potassium iodide, forming iodine, which is a dark brown liquid. That is it. And the equation is there, it is clear. When you are writing iodine, endeavor to put I2, because we said these halogens of group 7 exist as diatomic molecules. We looked at this. This is also important. In fact, last year in UNEB, this question was there. It was there, I remember. Reaction of chlorine with nonmetals, particularly phosphorus. We looked at this. Let's review. Chlorine with phosphorus, it forms two chlorides. It forms two types of chlorides. This one is phosphorus 3 chloride. When I say phosphorus 3 chloride, I mean phosphorus is using a valence of 3. And remember, the valence of chlorine does not change, it is 1. So when I say phosphorus 3 chloride, I mean the valence of phosphorus is 3 and the valence of chlorine is 3. So that becomes the correct formula of phosphorus 3 chloride. However, when you are writing phosphorus, you can write them as 4 atoms, or you write just P as 1 atom. But when you write it as 1 atom, to balance it, you will need to put 4 behind. You need to put 4 behind here. That is where you need to put a 4. So you can put a 4 behind there and you don't put this one. You remove this one. Phosphorus plus chlorine, the product is phosphorus 3 chloride. So we are saying when a piece of dry phosphorus, which is yellow, is lowered into a gas jar of chlorine, it burns spontaneously, giving off white fumes of chlorides of phosphorus, mainly phosphorus trichloride. But we are saying even phosphorus 5 chloride will be formed in the process. So when chlorine, and this is the same thing that happens with oxygen, remember, when phosphorus burns in oxygen, it also forms 2 oxides. There is phosphorus 3 oxide or phosphorus trioxide, then there is phosphorus pentaoxide or phosphorus 5 oxide. So keep remembering that chemistry. To balance, you put a 4, and that makes chlorine atoms 12, and you also put a 4, that makes phosphorus atoms 4. So for phosphorus, you write it as 4 atoms. So this is the equation for phosphorus 5 chloride, meaning phosphorus here is using a valence of 5. Okay. This one we looked at it. I just want to remind you that we also looked at this action of chlorine on iron 3. Action of chlorine on iron, we said the product is iron 3 chloride. Take note. Chlorine, when it reacts with iron, the product is iron 3 chloride, and it is formed as black crystals. When we ask for the observation, you say the iron wire grows red hot and forms black crystals, and the black crystals are of iron 3 chloride. But however, I say with iron with hydrogen chloride, remember you confused this in the test. Iron with hydrogen chloride, the product is iron 2 chloride plus hydrogen gas. Uses of chlorine we saw is used in manufacture of organic chemicals. It is used to sterilize water guard. From water guard, I told you the major substance that is there is chlorine. The major substance there is chlorine. Then the other use, it is used as a bleaching agent. So the uses, you will look at them. So I came prepared to discuss with you this part, and this is where we are now. The gas is hydrogen chloride. So that is our subheading now. Hydrogen chloride gas. Hydrogen chloride gas. How is it prepared in the laboratory? The first thing you should know is hydrogen chloride gas is acidic. Yes, it can be formed by direct combination of hydrogen and chlorine, and you form hydrogen chloride gas. That is by burning hydrogen in chlorine gas. But in the laboratory, we don't use that method. In the laboratory, we prepare hydrogen chloride gas by using sodium chloride and concentrated sulfuric acid. So if you have a notebook there, you can note it somewhere that hydrogen chloride is prepared in the laboratory by using concentrated sulfuric acid. I repeat, sulfuric acid must be concentrated, and common salt. This is sodium chloride. This is sodium chloride. So the two reagents that are used to prepare hydrogen chloride gas, I repeat, the two reagents are concentrated sulfuric acid and sodium chloride. No student of chemistry must ever forget that. Should ever forget that. So, since we have agreed that hydrogen chloride gas is acidic, by the way, remember when you are preparing carbon dioxide, you say pass the gas in water to remove hydrogen chloride fumes. So hydrogen chloride fumes, it means when they are dissolved in water, they give you hydrochloric acid. And when you have concentrated hydrochloric acid and you open it, it starts fuming. And those fumes coming from it are for hydrogen chloride. So place sodium chloride in a flask and fit the apparatus as shown below. So this is, my sodium chloride is a solid, so it is put in a flask. I repeat, sodium chloride here is used in solid state. Sulfuric acid is a liquid, so it is put in the thistle funnel. Sodium chloride is a solid, so it is put in the flask. Then sulfuric acid is a liquid, so it is put in the thistle funnel. So we put sodium chloride in the flask, and then we add concentrated sulfuric acid through a funnel. Immediately we do that, then there will be fumes of a gas given out, and the gas will be hydrogen chloride. Now, since we have agreed that the gas is acidic, then we must dry it using concentrated sulfuric acid. I want you to note this, that all acidic gases are dried using concentrated sulfuric acid. We looked at carbon dioxide gas, which is acidic. Why is it acidic? Because you remember from oxides, our knowledge of oxides, we said acidic oxides are oxides of nonmetals. You get that? From our knowledge of oxides, we said acidic oxides are oxides of nonmetals. So carbon dioxide is an oxide of carbon, which is a nonmetal, so it is acidic. Sulfur dioxide is an oxide of a nonmetal, so it is also acidic. So we are saying hydrogen sulfide also. So all acidic gases, chlorine, sulfur dioxide, carbon dioxide, hydrogen chloride. Now, I've given you a hint. I've given you 4 gases that must be dried by concentrated sulfuric acid. So when we ask about preparation, you already have the answer. So concentrated sulfuric acid, you add it, and fumes of hydrogen chloride gas will be seen, and that gas is dried by passing it through concentrated sulfuric acid. Now, when we do that and dry the gas, we finally collect it by downward delivery. You people, why should you fail a question about preparation of a gas? I've told you many times, you need just 2 substances that are reacted together. You need to know the drying agent. You need to know the method of correction, and you get marks. So effervescence occurs and misty fumes are observed. The misty fumes, you have said, they are for hydrogen chloride. The gas is passed through a wash bottle containing concentrated sulfuric acid to dry the gas, and it is collected by downward delivery since it is denser than air. Then finally, you must write the equation. Now listen to me, and listen very well. The acid we use is concentrated sulfuric acid. That means there is no water in it, or little water. There is either little or no water. So the state we give it is liquid. If it was dilute, then the state would have been aqueous. Sodium chloride is used as a solid. So this equation, you remember the other equation I gave you, the other one for preparation of nitric acid. We treat this one in the same way, because preparation of nitric acid, remember, we use the potassium nitrate and concentrated sulfuric acid. The product was potassium hydrogen sulfate plus nitric acid. Here we are using sodium chloride. We can also use potassium chloride, by the way. Sodium chloride, which is in solid state, plus concentrated sulfuric acid, the product is, please, I repeat, the product, when we are preparing hydrogen chloride and nitric acid, the product is hydrogen sulfate. So here the product is sodium hydrogen sulfate, then plus hydrochloric acid. Sodium hydrogen sulfate plus hydrochloric No, not hydrochloric acid, hydrogen chloride gas. Hydrochloric acid is obtained when this hydrogen chloride gas is dissolved in water. So the state for sodium hydrogen sulfate must be a solid, because there is no water, there is nowhere where water is coming from. We are using concentrated sulfuric acid, which is a drying agent. And we are also using solid sodium chloride. So there is nowhere where water is coming from to form sodium hydrogen sulfate plus hydrochloric, plus hydrogen chloride gas. Note, sodium chloride is used because it is cheap and readily available compared to potassium chloride. The reaction proceeds in the cold, though a further yield is obtained in the industrial process. The sulfate is not obtained under laboratory preparation conditions because its formation requires a higher temperature, but it is obtained in the industrial process. So we are saying there is no sulfate formed here, but instead we form hydrogen sulfate. Let us look at the chemical test for hydrogen chloride gas. When the gas is bubbled through water, or when the gas is bubbled through a solution of silver nitrate, acidified silver nitrate solution, it forms a white precipitate. The white precipitate formed is silver chloride. Why is it like that? Remember, all chlorides are soluble except there are two chlorides which do not dissolve in water. Who can tell me? Someone tell me about the solubility of chlorides. There are two chlorides which do not dissolve in water. Save my time. There are two chlorides which do not dissolve in water. All chlorides are soluble except there are two. Someone tell me. Kathy.
Silver chloride and lead 2 chloride.
Silver chloride and lead 2 chloride, correct? But lead 2 chloride is soluble in hot water. So since silver chloride does not dissolve in water, whenever it is formed as a white precipitate. That's why when we are doing the test for hydrogen chloride gas, we bubble it through a solution of silver nitrate and nitric acid. Yeah? When we do that, such that silver chloride is formed, when silver chloride is formed, it appears as a white precipitate because it does not dissolve in water. So the test for hydrogen chloride gas is that it forms a white precipitate when it is bubbled through an acidified solution of silver nitrate. The role of nitric acid is to acidify the solution of silver nitrate. I repeat, those who are noting down something, the test for hydrogen chloride gas, we say when the gas is bubbled through a solution of acidified silver nitrate, it forms a white precipitate. And the white precipitate is silver chloride, because we have agreed silver chloride does not dissolve in water. And this is the equation. The valence of silver is 1. So this is silver nitrate plus hydrogen chloride gas, and the product is silver chloride plus nitric acid. This silver will react with the chloride here, form silver chloride, and this hydrogen will react with the nitrate to form nitric acid. And that is it. So the other reaction, number 2, is that the other test number 2, when we were looking at ammonia, we said ammonia forms dense white fumes with concentrated hydrochloric acid. So I've told you, from concentrated hydrochloric acid, when it fumes, hydrogen chloride fumes are formed. So hydrogen chloride gas also forms dense white fumes with ammonia, forms dense white fumes with ammonia gas. And the dense white fumes are of ammonium chloride. So hydrogen chloride forms dense white fumes with ammonia gas, and this is the equation. Remember the other reaction we saw when it is put in a cube, a glass cube. This is ammonia plus hydrogen chloride, and the product is ammonium chloride. But remember, ammonium chloride has properties of sublimation. It can sublime. So it can be formed as a gas, but on cooling, it will form ammonium chloride, which is a solid. Let us look at physical properties of ammonium chloride, of hydrogen chloride gas. It is a colorless gas with an irritating, choking smell. It forms, since it is acidic, it forms misty fumes in damp air. In damp air, a damp air means wet air. In damp air, as tiny droplets of hydrochloric acid. I've already told you, when hydrogen fumes, when hydrogen chloride is exposed to air, to water, it will dissolve in water, forming hydrochloric acid. It turns moist blue litmus paper red, you know, because it is acidic. It is also soluble in methylbenzene. Why? Methylbenzene is an organic solvent, and hydrogen chloride is formed. The type of bonding in hydrogen chloride is covalent. So meaning it dissolves in nonpolar solvents, like methylbenzene. Hydrogen chloride gas is denser than air. That one we all know. It is denser than air, so it is collected by downward delivery. It is very soluble in water. When it dissolves in air, it forms hydrochloric acid. This should be water. When it dissolves in water, it forms hydrochloric acid. That one I've already told you about it. There is this important reaction which we have already looked at, chemical properties. When hydrogen chloride is passed over heated iron, that one, remember we saw it when we were looking at reactions of chlorine. When hydrogen chloride is passed over heated iron, for this one, the product is iron 2 chloride. I repeat, chlorine, when it is passed over heated iron, the product is iron 3 chloride. But when hydrogen chloride is passed over heated iron, that's when the product is iron 2 chloride plus hydrogen gas. Please keep remembering that and don't forget. So for today, I will end here. Those who have come late, you will ask for the recording because the lesson has been recorded. We have 2 minutes. We can use them if there is any question from either here or the test. You can ask. I think in the next lesson I will do corrections for the test because I had not finished marking some people. Okay. Oh, but our corrections we did, yeah, corrections we did last week. So we are not doing corrections anymore.